in here and put it right there. So now I can bring in my oxygen here and my oxygen here. So there's my 2 half-filled p orbitals on my oxygen. One goes to this sigma bond and one goes to this unhybridized p orbital. And now I've created my double bond in here. So this is my double bond. Okay, and that's what my valence bond diagram looks like for carbonate. And let's just redraw our Lewis structure because we have our trigonal planar. So this would be C, and then we'll have our double bond to our O, and then our single bond to this O. Put it in brackets. Put this in brackets. Okay, so the order you do in these in really doesn't matter. Sometimes it's easier to go right from this to your valence bond diagram and then do this last. The order doesn't matter as long as you know what the shapes are and what it is they look like. And what's really important is you know what's participating in here when you go ahead and make this. So if the last thing is the net dipole. Well, we know that oxygens are negative compared to carbons. And because we're completely surrounded by negatives, we have no positives. Your net dipole here is 0. And this is non-polar. Okay? All right. Let's do have a look at propene, and then we're going to do 2 triple bonds, and then we're going to be done with this. Okay? So let's do, because I want to give you propine to do after as an example, which is, so if we do propene, you'll have a pretty good idea of how to do propine. Okay, so propene. So we have a C to a C to a C, and the propene means you have a double bond in there somewhere. So I don't care where you put it. Let's put it here. Which means we need an H here, 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 and then this will single bond. Okay, so we have 3 carbons now. So what do we notice? Well, we notice that this carbon has 4 single bonds. So if we cover these up, 1, 2, 3, 4 single bonds. Cover this one up, and this one, this carbon has 1, 2, 3, and a double. This carbon has 1, 2, 3, and a double. So we'll call this C1, C2, C3. Okay, so C1 and C2 have the same hybridization. So we have a 2s with 2 and a 2p with 2. And their hybridization is 1, 2, 3 sigmas, 1 pi. 1, 2, 3 sigmas, and 1 pi. So we have if we promote, we have an S plus a P plus a P plus a P. This time we're only going to mix 3 in the pot. So 3 times sp2 plus a P. So that's what that one will look like. C3 is going to be, we already know that C3 is 4 singles. So C3 after you promote will be an S plus a P plus a P plus a P. But this time you mix all 4 in and you'll get 4 sp3s. So that's your hybridization for all 3 of those. So let's go to our Vesper shape. So we know that carbon 1 and carbon 2, because they're sp2s, we automatically know they're trigonal planar. We know that. This one, though, we automatically know is tetrahedral. So C1 and C2 are trigonal planar at 120 degrees. C3 is tetrahedral at 109.5 degrees. And we don't even have to look at Vesper anymore because we know that sp2s are trigonal planar, and we know that sp3s are tetrahedral, and the next one we do will just be sps. Those ones will always be linear. So they're nice because everything's just going to be in a straight line, pretty much for those ones. Okay, so if we were to look at drawing the Lewis diagram for this one, I'm just going to bring this up here. Okay, the Lewis bond diagram, we know that this has to be tetrahedral and this has to be trigonal planar. So what we can do is we have a C here, up to an H, up to an H, double bonded to this C. Okay, and that C now, so this is where things will get kind of weird because you have to draw this like that. It has to be trigonal planar. So that means our tetrahedral is going to be shifted slightly. So if we put this H down here, that means this carbon will be a C, up to an H, up to an H, up to an H. So that's why these long organic compounds, all these hydrocarbons, have these bent shapes like this, because we draw them in a straight line because it's easy, but its actual geometry, this is what propene really looks like. Trigonal planar, and then your tetrahedral. So drawing our valence bond diagram, let's start with this C. We're gonna have sigma, 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 dot in the pi. So that's this C, sigma, 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 pi, sigma, 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 pi. And then we're going to pop the H's on. Might as well do that now. And then let's bring in the other carbon. So it's going to have a sigma, sigma, sigma. And then let's dot in its pi to overlap right there. And then it has one H down here. This H is this H, and then the last C up top, let's switch colors here, orange. So you're going to have sigma, 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 and we know that that's this, so this bond here is this bond here, H, 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 and that's your valence bond diagram. Looks very similar to that. It's just replacing the sticks with these bubbles. Okay. All right, so let's do a couple triple bond ones, and then we're going to stop here. So this is 6 continued. Okay, because I'm going to post this for you as well, so you have all these examples. Okay, so number 7, what I want to do is HCN. Okay, so HCN, what do we have? We have a C with 4. We have an H here, and then we have an N, and we know the N has to bond to the C, so we're going to do 1, 2, 3, 4, 5, and then very clearly we can see this bond's here, and we're going to form a triple bond in here. Okay, so triple bond, what we need to do is we have a 2S with 2, and a 2P with 2. We're going to promote S plus P plus P plus P. But this time we only need 2 sigmas, and now we need 2 pi's. So think of your, in a triple bond, your 2 pi bonds kind of sandwich that single bond in between there. So we're going to get 2 SP's plus a P plus a P. Okay, so shape-wise, the only thing you can do with this is put it in a straight line. So we already know that SP's are linear. So this is going to be linear at 180 degrees. So it'll be an H bonded to a C, triple bonded to an N. And if we were to look at our net dipole on this, so positive, negative, the only thing it can do is go this way. So our net dipole equals 0. It's nonpolar. And we'll go back and do the net dipole for propane because I just realized I forgot to do that. But that one's pretty easy. Okay, so now our valence bond diagram. We're going to have our 2 SP's have to be linear. So we're going to put 1 here. And we're going to put 1 here. So that's this bond. and this bond. And then we're going to bring a P bond up here and a P bond up here. And those form our pi's. So there's sigma, pi, pi. And then your H goes here. And now what do you know about nitrogen? Well, nitrogen, again, going to your periodic table, nitrogen's S is full, but it has 3 singles in its P. So it has 3 unpaired electrons. So all 3 of its P orbitals need to participate. So we're going to draw that in. So this is going to get a little messy. So we're going to put one here. There's that one. And they are all on the same nitrogen, so they have to be connected. And then you put your s orbital pair. And that is your valence bond diagram. So triple bond, nitrogen with its pair here, H here. So these 3 are these 3, that pair, H, and that H there. Okay, can we just go back to look at this one for a minute? What do you know about all the hydrogens surrounding propene? They're all positive. So we already know hydrocarbons, we've done this to death. Hydrocarbons are nonpolar. And the reason why they're nonpolar is they have no opposing charges at all. They're filled with all these positive H's. So your net dipole here is 0 and it's nonpolar. Okay, so that one's pretty straightforward. Okay, the last one I want to do with you is carbon dioxide. Okay, and this is a special one in that when you draw carbon dioxide, 1, 2, 3, 4, O with 6, O with 6. What you notice now is something we have not yet seen, 2 double bonds. Okay, so think about this for a minute. What shape is carbon dioxide? Carbon, remember, double bonds count as single bonds in VSEPR. So we have 2 single bonds and no lone pairs. 2 single and no lone pairs is linear. So we know that this is linear at 180 degrees. Well, what hybridized orbitals are linear in shape? Not sp3s, they're tetrahedral. sp2s are trigonoplanar. SPs. So here's what we're going to do. Up here we made 2 SPs and 2 p orbitals we left out for pi bonds. They form a triple. But what we're going to do here is make 2 SPs and 2 p orbitals, just like this one, but these 2 go in the same direction to make a triple. And this one will go to this oxygen and one will go to this oxygen. So instead of taking your 2 p orbitals and going this way, we're going to make one go this way to bond with the O and the other one go the opposite direction to bond with the O. So we're going to flip it 180 degrees. Okay, so let's just draw. Okay, that's linear, and again, net dipole is 0 because you have no positive charges. So that should make sense because I think we all know that carbon dioxide is a nonpolar molecule. Okay, so let's hybridize this carbon. So we have a 2s with 2 and a 2p with 2. We're going to bump this up here, and we're going to have an S plus a P plus a P plus a P. So like we did up here, we're going to leave 2 of them out, spit out 2 SPs on the other side, plus P plus P. These here are linear. So 1 here and 1 here. So that's going to be this one is this one is this. And then up here, see where we drew 1p up above the sigma, 1p down below? We're going to draw 1 up above and put it here. But instead of putting the other one down here to make a triple, we're going to put the other one on the opposite side. So now we can create a double. So the hybridization for the triple bond is exactly the same as the hybridization for 2 doubles. So 2 doubles and a triple are the same hybridization. And then you're going to bring your oxygen. Oxygen comes in with 2 half-empty P's. So we're going to draw one here and one here with the 2 lone pairs, one from the P, one from the S. And we're going to do the same thing here and the same thing here. And that's your valence bond diagram for CO2. Okay, so remember, if we just go back to this here, we're going to add and 2 double bonds are the exact same hybridization. Okay, so I don't think I missed anything else. I'm going to give you no more than 10 practice questions to do. Go through and do them, and then we are done this unit. I'm going to be posting a quiz for you within the next couple of days. Okay, but I want to give you some time to work on this. So thank you very much, and good luck with this. If you have any questions, please email me.